an incredibly important, useful thing we're going to learn this year. This is something that if you go off to college or industry and end up doing mathematical things, you're going to find vector valued functions to be really, really important. Oh wait, have we started yet? Well, good for you. Yeah, and I cleared out a bunch of memory, so it should be good. Okay, great. So here's the thing. Okay, all vector valued functions is parametric equations. Okay, so whenever you start feeling like you're lost in space or you don't know what's going on, just always remember, hey, these are just parametric equations. That's all. But what makes them special is by turning them into vectors, we get this infinity of vector and matrix mathematics that we now get to apply. Okay? Because, there's an entire, when you go to college, you'll spend an entire semester learning something called linear algebra, which is, it comes after multivariable calculus, usually. And when you learn linear algebra, which isn't like ninth grade algebra, it's something very different, you're essentially spending the whole year working with matrices. And matrix mathematics is a very rich and useful way to do things, and where you get I'll just leave it like that, and so you get to apply all of that universe of matrix mathematics to vector valued functions, whereas you don't get to apply it to parametric equations because parametric equations aren't vectors, So anyway, that's why we're doing it. Vector valued functions is just like parametric. Let's go for it. First, I'm sorry. Okay. I'm sorry. I don't know why sometimes I try to do lessons by not having my notes, and then I suddenly get a hiccup, and now I'm like, lost. Yeah, not lost, but. Yeah, lost. Not lost, but I'm going, okay, what am I going to do next? Okay. First things first. Here it comes. Expressing vectors in IJ form. Okay? The first thing I want to introduce to you is this other way of expressing vectors. Suppose I have a vector v, and that vector is 2, 3. There's my vector, okay? And so if I draw that vector in standard position, I know that my initial point will be at the origin, and my terminal point will be at 2, 3. Great, there's my vector 2, 3. But now I'm going to express that vector as the sum of a bunch of unit vectors. I'm going to say that the unit vector in the x direction is called I. Now I'm going to call it I hat because that little caret on top denotes that it's a unit vector. Your textbook doesn't do I hat. Your textbook does bold-faced I. So your textbook is going to do this. This is the unit vector in the I direction. But again, I writing on a whiteboard don't really have access to bold-faced type. Okay? So there's I. So here's 2I. This vector is 2I, and then you know what I'm going to call this unit vector in the y direction. I'm going to call it j hat, or j. And so, do you see that if I add 2I plus 3j, here's j, j, and j, I get this vector. And so, rather than using component form, I'm going to say that this is 2I plus 3j. I'm not really changing anything. It's just a different way to write vectors and a different way to think of vectors.
Is this all the homework you see?
What's that?
Is this all the homework you tonight?
Yeah. Well, there's going to be a lot more. No, there's much more. Okay. So, okay, great. So that's IJ form. All right. So here. write vector PQ in ij form, where P is the point -2, -4, and the point Q is, oh, I don't know, 1, 2. Okay, good luck. Please get me vector PQ in ij form. This will only take you a minute. What is that, 3, 6? Okay. So that's it. How many people are getting 3i plus 6j? Or did I mess it up? So I'm good? Okay, so that's it. So I'm not like having you learn anything new. It's just a different way to express answers that you've already been getting. You know, instead of 3, 6, now it's going to be 3i plus 6j. Meaning that if I wanted to draw this guy, you know, if I wanted to draw this vector like this, I would just have to make sure I go, oh, okay, well that's 1, 2, 3i, and 1, 2, 3, 4, 5, 6j, you know? That's all. That's what that vector is, yes?
So we would do that, even if like the number was like 9 over rad 90, you would do 9 over rad 90i, whatever.
Yes, absolutely. So Andrew's going, what if it's some fraction of the unit vector? Then yeah, like if you had 6.5j, then it'd be 6.5j, or 3.25i, or whatever. Absolutely, yes.
So it has to be in standard form too?
Yeah, absolutely. Yeah, all vectors are expressed in standard form. When we express them in component form, that's assuming that the vector is in standard form. And we're able to do that because remember, a vector has no particular position. So since a vector has no particular position, let's just put them all with their initial points at the origin. And then we get to express them in component form. Okay, there's another thing I want to talk about before I go any further that again, people in my AP Physics class already know. And it's this idea that we live in a universe, and here I'll get it in the camera, you know, we live in a universe where phenomena in one direction is completely independent of phenomena in a perpendicular direction. Okay, and those of you who haven't had me for physics maybe have never learned this. You know, this idea that if this is a river, alrighty, and I point my boat directly across the river, and I have my boat going 3 meters per second, okay, and it's pointed directly across the river, and let's say this is a 15-meter river, then it's going to take you 5 seconds to get across. And it's going to take you 5 seconds to get across no matter how fast the current is going. If there's no current at all, you'll just end up right there, and it took you 5 seconds. If the current is going at 4 meters per second, then your net speed will be 5 meters per second, and you'll end up over there, but it still takes you 5 seconds to get across. Because the fact that you're going really fast in that direction has absolutely no influence on your progress in a perpendicular direction. And that's true for not just velocity, it's true for force, it's true for any vector quantity. Phenomena in one direction is completely independent and unaffected by phenomena in the perpendicular direction. I mean, if you've got some guy, let's say this is a football game, so this is the goal line. Okay, and this guy is running this way, and then some tackler comes and is exerting a force perpendicular to the guy's progress. Is he hindering the guy's progress at all? No, not at all. And the only way he can hinder this guy's progress is to exert a force with a component in the x direction. As long as this guy is exerting a force in a y direction, this dude will go at some angle, but his progress in the horizontal direction will be completely unaffected. That's why when you tackle someone in football, you have to do something to impede their motion in the horizontal direction, you know? So that's it. So that's why, since phenomena in one direction is completely independent of phenomena in a perpendicular direction, it becomes incredibly useful for us to express every vector in their x and y components, because the x and y components are completely independent of each other, you know? And in fact, that's what we call this guy. This guy is called the x component of the vector, and this guy is called the y component of the vector, you know? And we always want to do that with vectors. It makes it just a lot easier to deal with. Okay, so I just needed to make that little of aside for those of you who have not had me or don't currently have me for AP Physics. That's why we like to have the x's and y's separate, because they're completely independent of each other. They don't affect each other at all in the least. And why is it? Because that's the universe we live in, baby. There's other universes where that's not true, but it's true in ours. And that's all that really matters. Okay, great. Next thing. I need to show you what a vector valued function is. Vector valued function, or as I like to call it, a VVF. Okay. Let's say I had a parametric equation that looked like this. X equals t squared, and y equals t plus 1. I'm going to make it very, very simple. Let's say there's my function, my parametric equation, okay? All I have to do, and this is x of t, if you will, and y of t, okay? All I have to do to turn this into a vector-valued function is say, okay, I'm going to have the collection of vectors r of t, and by the way, r of t is the variable we use for a position. R of t is position, v of t is velocity, a of t is acceleration, but for some crazy reason, r of t is position. I would have used s of t, but our book uses r of t, whatever. R of t ends up equaling x of t I plus y of t j and so what you get when you graph this vector valued function is the collection of vectors given by x of ti plus y of tj. So for example, let's say t goes from, I don't know, -2 to +2. Let's say t goes from -2 to +2. Alrighty? Then when t is -2, and I can still treat this like a parametric with the 3-column table of values. When t is -2, I get an x of 4, and I get a y of -1. When t is -1, 1, and 0. When t is 0, 0, 1. When t is 1, 1, is 1, 1, 2, that's 3, and then 4. Okay, so now I can graph this. Okay. What you're supposed to picture is a collection of vectors whose terminal points are given by these points. So with the parametric equation, you'd be plotting 4, -1, 1, 0, 0, 1, 1, 2, and 4, 3. You would be graphing these points if this were parametric equation. But since it's a vector-valued function, you're supposed to actually picture in your mind a collection of a collection of vectors. You're plotting this vector, oh my God. Hey, don't draw what I just drew. I think what's happening is I'm like really aware that I'm videotaping myself, and I'm afraid I'm gonna make mistakes. I don't know why, I don't usually care. But I'm really concerned about that today. It's weird. I don't know what my problem is. Okay. So, what was it? 4 comma negative 1, 1 comma 1. Okay. These are vectors in standard position, so I need to be drawing my vectors from the origin. Here we go. So it's going to be this vector, that vector, that vector, and that vector. So a vector-valued function is a collection of vectors. But weirdly enough, even though a vector-valued function is a collection of vectors, when we draw the vector-valued function, we still just draw the terminal points of the vectors. So when you draw your vector-valued function, it looks the same as when you were, making a parametric equation. I mean, you haven't changed what you do. You're supposed to just change the way you think about it. Where now it's not a collection of points like a parametric equation would give you. It's a collection of vectors. But you still only graph the terminal points of these vectors, Only graph the terminal points. So that's all you got to do on these, guys. So let me run through what I'm going to have you do on a problem that you're about to do, okay? I'm going to give you a vector-valued function. And then part A, you're going to graph it. And remember, you only graph the terminal points, but in your mind, you're thinking of them as vectors. And then B, you're going to get an expression for V of t and A of t. And now these are vectors. These are a collection of vectors. So I have to put the little vector symbol above them. And the way you get V of t and A of t is the way you would expect. Just take the first and second derivatives. But luckily, because the x and y axes, the x and y coordinates are completely independent of each other, all I got to do is just take the derivative of the x and the derivative of the y totally separately. So let's go for it. Hey, V of t in this case is going to be r prime of t. It's the derivative. And when I take the derivative, I just take the derivative of the x and the derivative of the y. So that's my collection of velocity vectors. And then finally, acceleration is going to be the derivative of the velocity vector-valued function. And again, I can just get the derivative of the x and the y separately. The derivative of 2t is just 2. And the derivative of 1 is 0, so there is no j component. If you want, you can put 0j, but you don't have to. Just put 2i. Here's the next step. They're going to ask you, I'm going to ask you a question. Find the particle's speed and direction of motion at the given value of t. So I'm going to say, find speed and direction of motion. Yeah, exactly. As a unit vector at t equal 1. And I'm going to actually ask you to draw the vectors at that point. Draw the vectors at that point. So here's what we're going to do. First of all, let's find, as Daniel said, let's just find the velocity at v equal 1, and then let's find the acceleration at v equal 1. Okay? So I'll do that, I don't know, I'll do that over here, down here maybe. The velocity at t equal 1, I'm just going to stick a 1 in, and I get 2I plus j. That's the velocity at 1. All right, do they want the acceleration? No, they don't want the acceleration. Well, I want the acceleration. So maybe I should say, find speed and direction of motion in unit vector at t equal 1. Draw vectors of v of 1 and a of 1. Okay? Because I want to get the acceleration at 1 as well. The acceleration at 1 is 2i, because that's going to be acceleration for any point. So here's what I'm kind of getting at, okay? Here at this point, at t equal 1, right? Because at t equal 1, I'm at 1 comma 2. I'm at this point, t equal 1. You know, t equal 1 is right there. I can draw the velocity vector and the acceleration vector right at that point. My velocity vector is 2 comma 1, which means I go over 2 and up 1. So this is literally my velocity vector. This is v of 1. And then I can draw my acceleration vector. My acceleration vector is just 2i. So this is my acceleration vector. Alrighty. First of all, does that make sense that your velocity would point in that direction? Essentially, what's the relationship between the direction of the velocity vector and your graph? Like, what does that velocity vector look like to you guys?
Increasing.
Okay? But I'm just saying, relative to the graph, like if I drew the graph like this and the velocity vector is going like this, or if I drew the graph like this and the velocity vector is going like that. What's that? Say again?
Tangent.
Yeah, you guys okay? That's the tangent. Your velocity vector will always be tangent to your graph, because it is the first derivative. I mean, you're plugging into the first derivative. So yeah, it'll be tangent to the graph. But the length of the velocity vector tells you how fast you're going. You see? And the acceleration vector, do you notice that this is a parabola? And when I throw something in the air on Earth, you know that these objects take on parabolic trajectories. And when I throw something on Earth, it has a parabolic trajectory because the force of gravity is constant and downward, right? So do you see that with this parabola, your gravity would have to be acting horizontally? If you're a horizontal parabola, then you're going to get a constant force horizontally, which means a constant acceleration. So that tells me at every point, you know, the acceleration is going to be the same, right? This is your acceleration, this is your acceleration, just as it is when you throw something on Earth. Throw something on Earth, it has a parabolic trajectory, constant acceleration. Same thing with this parabola, okay? So definitely one of those skills I want you to have is to be able to draw a graph, a parametric graph, but it's a vector valued function graph now. You don't need those red guys, all you need are the points, but I want you to be able to draw me the velocity and acceleration vectors on the graph. Okay? Let me see. Finally, they said find the speed and direction of motion as a unit vector. Let me do that over here. This is all leading up to you guys doing a problem like this. And by the way, this is like number 5 of tonight's homework. This problem is like problem number 5. All of those problems, I think it's like 5 through 8 or something. Okay. Let me do part C. Okay, find the speed and direction. Well, if my velocity vector is 2I plus j, I hope you see that just like with parametrics and vectors, you can get the speed by getting the magnitude of the velocity vector. And that's going to be the square root of 2 squared plus 1 squared, which is radical 5. That's the speed. Your direction, let me remind you what we learned yesterday. If you have a vector that's 2 comma 1, or generally if you have a vector that's a comma b, you have the vector a comma b, then the direction is going to be, or rather the slope, let me see, what do they want? I'm so sorry. No, direction of motion. Oh, I don't even have to do it. Oh, as a unit vector. Oh, I was thinking of something else. I'm so sorry. They want it as a unit vector. So they want v hat of 1, which means it's just going to be 2I plus j over rad 5, or 2 over rad 5I plus 1 over rad 5j. That's all they want. Okay. Yeah. Or I think, let me think, what does the book do? Wait, speed and direction of vector. Oh, I know. I'm thinking of part D. Okay, so there we go. There's my unit vector if they want the direction. So I think what they say by, wow, you guys, I'm so sorry. I almost want to just turn off that machine, but I won't. They say, so the direction of motion is that, the speed is that. Write the particle's velocity at that time as the product of its speed and direction. So what they want me to do is this. Part D, they want me to do this, that v of 1 is equal to the speed multiplied by the direction, which is 2 radical 5I plus 1 radical 5j. So it's kind of a weird, freaky way to do a problem, in my opinion, where you're doing speed multiplied by the unit direction vector. That's what they want you to do. Okay, whatever. But anyway, part C is for me the more interesting one. More interesting still is just knowing what the speed and the direction are. This is the speed, this is the direction. When they say direction, they mean the unit vector in the direction. And that's the speed. And then if I want, I can multiply speed times the unit vector in the direction, and then that's my velocity vector, which is what I started with. Okay, well, it's time for you guys to do a problem like this. Here it comes. For x of t equals x to the third power and y of t equals t minus 1, a graph for negative 2 is less than or equal to t, which is less than or equal to 2.
You mean t cubed?
Yeah, t cubed. I'm glad no one watches these videos.
Mr. Morrison watches them.
Noel watches them.
Really?
Right?
A lot of kids in Morrison's watch them.
Mr. Morrison himself even said that it was
He said that you do a really good job.
That's so nice of him. He is so nice. Hi, Noel. Okay, here we go. Graph. Okay, you're gonna graph this. You're gonna. What am I gonna see here? Get v of t and a of t. Okay. C. Oh, I'm sorry. Get v of t and a of t, and then graph v of. Just 1 second. 2. So I want 2, huh? Graph v of 2 and a of 2 at the point x or r of 2. Alrighty. And then part C, I'm going to want you to get speed and direction. The speed and direction of motion at t = 2. That is, I'm going to want you to write your velocity as the speed multiplied by the unit vector. That's all I want you to do, and that's good enough. Okay, good luck, you guys. And I'm gonna have to do this myself. I'm hoping it worked out right. I just made this thing up.
This is gonna be.
I'll be really embarrassed if it didn't look good. And you can't go wrong doing a 3-column, even for vector valued functions or parametrics. Doing a 3-column table of values, you'll never go wrong. Maybe I should have done all that stuff for V of 1.
No,
Is it okay? Okay. Now, V of 1 is more interesting. Hey guys, can I change this? This
Yeah.
graph, do V of 1 and A of 1 at the point R of 1. Change everything to 1, because it's just a more interesting graph. I hate when the acceleration and velocity are virtually parallel, where that's not going to be true for that. Okay, good luck. 3 and up 1. And my acceleration is 6. Okay, you guys, first of all, did you graph and get like a sideways cubic that looks like that? And then you get at that point 1, 0, not anywhere else. You've got to actually graph it, you know, at this point here. At the point 1, 0, did you get a velocity vector of 3, 1 and an acceleration of vector of 6, 0? Okay, if that's what you got. And then also, do you see how visually you can see that your acceleration is just bigger than your velocity? Whereas here your velocity was bigger than your acceleration. That's kind of giving you a sense that, hey, this is something that's really accelerating a lot, you know? I don't know, it's just visually gives you some information. Any questions or issues on parts A and B? Yes?
When we draw the vector for a velocity, do we draw the unit vector?
No, when you draw the velocity vector, you actually draw the actual vector. So my vector here, I went over 3 and up 1. Yeah, this vector here, I went over 2 and up 1. Yeah, definitely, you want to draw your vector as it is. So if I give you a velocity vector that's humongous, you're stuck having to draw some humongous vector. You know? But then again, so someone can look at it visually and go, hey, that thing's going fast. And then finally, if you got the speed of radical 10, then your unit vector is 3 over rad 10, 1 over rad 10, you know, I, j. Whoops, I wrote my j wrong. It's a backwards j, you know. And then you multiply by the speed. So our textbook, for some stupid reason, wants you to express your velocity as the product as the scalar, you know, product of radical 10 times the unit vector, you know, 3 over rad 10i plus 1 over rad 10j. Hey, how many people got this right, the graph with the vectors? Okay, good, good. That's like the important thing, you know. Okay, and then if you're able to get the speed, that's huge. And then if you can express it like this, well, you know, well, now you know how if you couldn't do it the first time. Hey, any other questions or issues on this? Our vector valued functions. Okay, then let's do another problem. Let's deal with these vector valued functions. Sometimes you're given stuff like this. Here, we go number 537. Huh. I wonder why I only signed one of these. That's freaky. Why wouldn't I assign 17? Just 1 second. I did assign 17. I forgot to write it down. How freaky. Hey, on tonight's homework, if you wrote it down, please add number 17 to your problem list. my bad. Okay. So here we go. Suppose dr dt equals t to the third power plus 4ti plus tj. And suppose I told you that r of 0 equaled I plus j. Get r of t. I'm going to show you how to do this, then I'm going to have you guys do one on your own. Here's what we're going to do. Let me wait till you guys write this down. R of t is going to be the antiderivative of dr dt, right? So let's go ahead and take the antiderivative of these guys. But here's the thing, the x and y's are totally independent of each other. So ordinarily when I take an antiderivative, I have to sprout a constant of integration. But what's going to happen here and here? Well, when I take the antiderivative, I'm going to have 1/4 t to the fourth plus 2t squared plus the constant of integration, and I'm going to have to call that C1 because I'm going to get a different constant of integration for the j component. So this is going to be plus 1/2 t squared plus C2 j. And now I'm going to have to find both the I and the j components of my constant, of integration. So let's go ahead and plug in r of 0. So r of 0 equals I plus j, which is going to equal 1/4, 0 to the fourth plus 2 times 0 squared plus C1 I plus 1/2 0 squared plus C2 j. I think it's pretty obvious. What ends up being my C1 and my C2? Yeah, 1. I get I plus j equaling C1I plus C2j. Okay, so I get C1 equals 1 and C2 equals 1. And so now I get my final answer. R of t equals 1/4 t to the fourth plus 2t squared plus 1 times I plus 1/2 t squared plus 1 times j. That's the process. It's just the same old process we always used. So hey, let me have you guys do one. Okay, what if I gave you this? R prime of t is equal to sine of ti plus e to the 1/2 tj. And I told you that r of 0 was equal to 2I plus 2j. Get r of t. Good luck, you guys. Good luck. Take the antiderivative, get your constants of integration, and then you win. And we're gonna do one more problem, like number 32. Okay, you guys done yet? Are you done, Fatima? Oh, then I'm not gonna start if Fatima's not done. At this point, you guys should be there. You should have taken the antiderivative of sine of t and gotten negative cosine, and the antiderivative of e to the 1/2 t and gotten 2e to the 1/2 t, and then plus your constants of integration. Are you guys there?
Yes.
Okay, and then did you stick 0 in for t and set that equal to 2 comma 2, 2i plus 2j? Okay, let's go for it. R of 0 equals 2i plus 2j, which equals negative cosine of 0 plus c1i plus 2e to the 1/2 times 0 plus c2j. So do you see 2i plus 2j equals, cosine of 0 is 1, right? So I got negative 1 plus c1. And the 2e to the 1/2, that's 2. Are you guys okay with that? So do you see, what should C1 be?
3.
Yeah, 3. You can get it just by looking. Or if you need to do this, if you need to make sure that 2 equals negative 1 plus C1, and so 3 equals C1, if you have to go through that process, that's fine as well. But however you slice it, you should end up with C1 equaling 3. What should C2 be? Hopefully you're getting 0, because 2 has to equal 2 plus C2. So I get C2 equals 0. And so you get your final answer. R of t equals negative cosine of t plus 3i, and then plus e to the, or 2e to the 1/2 t j, because there's no constant of integration there. Did anyone get that answer? Okay, 2 of you, 3 of you, good. I taught it then. I did a good job, if only 2 or 3 people got it right. Okay, but now is there any question or problem? Is that good enough for you to do a problem, a third problem that you're going to do for homework 15 and 17?
Yeah.
I hope that's good enough. Any questions on this? Okay, then in our remaining 4 minutes, there's one more type of problem I need to prepare you for, and it's a problem like number 32. So, and I'm just going to show you a problem like 32. Problem like number 32, okay? You're going to get an expression for the path of a particle, the expression for the position of a particle, r of t, and that position is going to be t squared plus ti plus t to the 3rd j. So there's my position particle. Please, position of the particle. Please write that down. Okay. Here's part A. At which times is the horizontal component of velocity 0? At which time or times is the horizontal component of velocity 0? Well, first things first, I better get an expression for the velocity. V of t is going to be the derivative of r of t. Ignore that alarm, whoever's that was. So I get this. All right. But if it's the horizontal component of velocity that has to be 0, I hope you see that all I care about is the I component. So I'm going to put that the horizontal component, x prime of t, if you will, is going to be 2t plus 1, and that equals 0. So t equals -1/2. If they're going to ask you about the horizontal component of velocity, all you're going to care about is that guy. Next, they're going to want an expression for dy dx. And I got to tell you, if they want dy dx, you're going to have to treat this like parametric. Okay? dy dx, you're going to revert to parametric. Because remember, vector valued function is just a convenient way to express parametric. But a vector valued function is just a parametric equation. So I'm going to do this dy dt stuff. So I'm going to have 3t squared over 2t plus 1. There it is. There's my expression for dy dx in terms of t. Just the derivative of the y component over the derivative of the x component with respect to t. And then part C, if they want an expression for, d squared y dx squared, just a second. Hey, you're just going to do this thing. You're going to do the derivative with respect to t of that guy divided by dx dt. So I just want you to be aware, 32 is an easy problem. Just do it like this. Well, good luck tonight. Sorry I really muddled through this whole lesson, but good luck on tonight's homework. And I'll be here today after school if you want to stop by and be here while you do the homework. Are you going to turn it in?